In this video, I'm going to do a teardown of an Amazon Echo Dot to look at it from a product development standpoint. We're going to be looking at every detail, including the electronics, the enclosure, any other mechanical parts, and the packaging itself. And I'm going to share a secret with you. If you want to learn how to develop your product, one of the best ways to do that is to tear apart other products similar to your own and see how they did it. Hi, I'm John Teal. I'm an electronics design engineer and entrepreneur who brought my own product to market. And now I help entrepreneurs, startups, inventors, makers, and small businesses develop and sell new electronic products. Okay, let's get started. So here we have an unopened Amazon Echo Dot that I'm going to open up now and see what it takes to make this thing. So everything is separated in this paperboard insert. Let's pull out the USB charger, the USB cord, the dot itself, and the instruction manual, or instruction manuals. And then we'll just now take off the plastic protective layer that's over the dot itself and the USB charger, just to prevent it from being scratched up during shipping. This is a full color box with graphics and text printed on 5 sides. The box is made out of a paper board, so it's basically like a thick paper. And it's got a peg hook here for hanging it in a retail store. And it's got a piece of tape here to seal it shut. Then we have the inner insert that is also made of paper board. And it's designed obviously to hold the separate pieces and keep them separate. So you've got the dot itself, the USB cord, and the USB plug, and the instruction manuals. Each fit in a different compartment to obviously hold them secure, and then also to make sure nothing gets scratched up. And you can tell this is basically just looks like one piece of paperboard that's folded and glued to make the 3 different compartments. And we have the 2 instruction manuals. For a lot of products, this can be reduced down to 1 instruction manual. Then we just have the plastic covers for both the dot itself and the USB power supply, and these are basically just to obviously prevent it from being scratched. Obviously, minimal cost for these, fractions of a penny at any type of decent volume. And then so there's looks like 3 pieces, the plastic covering. Then we have the USB cord. This is something that can be purchased. Obviously, you just purchase this off the shelf from a supplier. And then the power adapter as well. If your product uses a power adapter, I would highly recommend, if possible, using a USB power adapter or some type of standard power adapter. So you could just purchase this directly from a supplier that's already pre-certified. Obviously, anything that plugs into an AC outlet requires UL certification to be sold in the US, which is pricey. So it's best if you can just purchase the AC to DC adapter as a pre-certified off-the-shelf component. Especially with the this is a USB, it takes 110 volt AC and outputs a 5 volt DC signal. So that's the most standard and the most common. It's just got a micro USB plug on the one end. Okay, then we have the Echo Dot itself. Has 4 buttons. It's got the power button, the volume up and down, and a mute button. So, and then on the back, it's got the USB port, and then it's got an audio plug. If you want to, the speaker is very minimal in the Dot. It doesn't have near the audio performance as the Echo. So this is fine for just asking questions and maybe a little bit of music, but I wouldn't recommend this if you're really into audio quality. You're going to need an external speaker to hook to this. Okay, so now we're going to tear this apart and let's see what it takes to make one of these things. Okay, we're going to take this apart we're going to first peel off this back padding. Just going to get a little knife and get under there, and then once I get a lip, I can just pull it back off. It's just glued on. This most likely, not, you can tell it's definitely not a glue. It looks more like a custom cut piece of double-sided tape. In most cases, I found it's better to use a double-sided adhesive like this or tape than it is to actually use some type of liquid glue. From a manufacturing standpoint, dealing with glues can be quite challenging and messy, so it's not something I generally recommend. So now we've got 4 screws that we have to take out, but there's still a transparent covering here that I'm going to pry off now. There we go, got the edge of it. And then once again, this is just glued on there. Okay, so we've got 2 pieces. We have this, it looks like a silicone rubber sheet. This is something you could probably, this has got printing on the back, but this is something that you could probably find off the shelf somewhere. You would need to customize that. That's one nice thing about the shape of the dot is it's circular, which makes like this piece, these 2 pieces here would be something you could surely find off the shelf. If not, there's not a whole lot of customization involved, so there shouldn't be much setup cost or anything associated with these compared to injection molds for the plastic case. And you can tell from this case, this is most likely a polycarbonate plastic is what this is made from, which tends to be the most common plastic I've seen for more higher end electronics. ABS plastic is the other common type of plastic that tends to be more associated with use on toys and maybe lower quality electronics. But polycarbonate has a really nice appearance, much nicer appearance than ABS, and it has a high impact strength. So if it drops, it doesn't crack easily. Okay, so now that we've got those off, we can use a screwdriver to take out these 4 screws. And one more. Yeah. This version of the Echo is a lot easier to disassemble. The first one was a little more challenging. There's a lot more glue involved in getting it apart, and the bolts were more on the inside versus the outside. So this is a lot easier to get to. So now that we've got those 4 screws out, it should just basically fall apart here. Okay, so we've got, this, pretty sure this pops out. So this plastic piece is the speaker. Looks like the contacts are there, and the speakers, I suspect, embedded in it. This is obviously not a very standard speaker. This is most likely obviously a custom designed speaker that was designed to maximize the audio quality that you could get in such a small amount of space. So this looks like it's made of at least 2 pieces of injection molded plastic. Looks like you have the top piece, and then the bottom is like a flat piece that it fits on and seals that closed. So, okay, we'll look at that a little bit more later. Let's see, we've got one of the boards. There are 2 boards in here. This big metal piece is basically just to give the product some weight. Obviously, you don't want to. Obviously, sometimes weight makes a product feel of a higher quality, So I'm pretty sure that's why this big piece of metal was added, just to give it a little bit of weight, make it have a higher quality feel, and then make it where it most likely doesn't vibrate and make any type of annoying rattling while playing. Not that you're going to get a lot of bass out of this, but nonetheless, that's what it's for. You can see here you have the micro USB and the audio output plug, and those are both soldered right onto the PCB, and then those mount up with the holes in the back of the enclosure. There are two ways to do connectors, and typically the way they've done it here is the simplest, best way, and that's to have them mounted on the printed circuit board, and then they align with the necessary holes in the enclosure. The other option is you can have these be wired connectors. So then you would just have the connector would be sort of free moving, and then there would be wires that connect it to the board, and then that gives you more flexibility in where you're able to place it. So if for some reason you wanted a connector located somewhere that wasn't going to be in line with the printed circuit board, obviously when you mount it on the printed circuit board, you're pretty much limited to, you've got to have the connectors on the outside are going to be somewhere along the plane of that PCB. So wired connectors give you more flexibility, but they add more assembly complexity. It's, just another step of those wires having to be connected, and that having to be the connector being placed in the right hole, versus when you have them on the board, everything just kind of automatically aligns. Okay. Here. Okay, so now we're going to, the only thing holding these together is this little ribbon cable. So I'm going to just pop up this little connector there, and that comes right out. And then you can pull these apart. So it looks like, there, it just pops out. Okay, so we've got there's one board. And we have a silicone insert. Once again, I suspect it's just to dampen out any type of vibrations and prevent any type of rattling. And then you have, looks like this custom spacer board, which has, you can see it's got the slots in it, and these are on the board below it. This is the main audio board. These are the microphones. And now we're just down to the top cover with the printed circuit board that's mounted underneath of that. Now let's see if I can push that through. And what you can see is on the main board, looks like another spacer piece of plastic. It's a spacer that sort of looks, let me see if it's stuck on the board or taped on the board, or yeah, it seems like it's taped on the board. But each of these are tactile buttons. They're basically just a piece of metal that's in the shape of a dome, and when you press down, it makes contact. So these are very low cost. More of the complexity with having such a button is the mechanical piece here. So when you press the button, you can see there's a little bump right there that presses down on the tactile switch. So the tactile switches on the PCB aren't really that much of an issue, but you can see you need something to hold the button cover. The button cover tends to be the more complex part to develop and scale for manufacturing, because, well, first of all, now you've got another piece of plastic, and as I talk about frequently, each piece of plastic requires an injection mold, and injection molds are expensive. So it's always best especially on your first version of your product, to try to minimize the number of custom plastic pieces. So you can see that there's 4 buttons. Each of these buttons is the same size, so the same plastic was used. They have they're printed, labeled different with different symbols on them, but those are the same. So that would be one mold for each of the buttons. And then you can see there's also the white piece that goes inside. That's another custom piece of plastic. Then you've got this piece here that, I don't know if you can see, that it looks like it's attached here, and goes out, and it's basically what gives each of the buttons a little bit of spring. So from what I'm seeing here, just for the buttons, you're talking about, you've got the button itself, that's a mold. This little insert with the bump is a mold. I'm not quite sure why those were done separately. To me, it seems like that could be all one piece, and perhaps that is maybe I don't know, they would be the same color. So this is either one or two pieces of plastic for the button, then a third piece for the piece that gives all the buttons a little bit of spring and helps to hold them in place. Then you have the top cover is also obviously another piece of injection plastic. Then you have this sort of transparent ring that goes around the outside. So that's just another piece. Even though this is a fairly simple product, relatively speaking, and very efficiently designed, very optimized to make it small and low cost, you can still see that most products, there's lots of little details. Think about just a simple push button requiring 2 to 3 pieces of custom shaped plastic. Okay, so now we are going to focus on taking a look at the 2 printed circuit boards, which is where all the exciting stuff is located, at least in my opinion as an electronic engineer. Okay, so we've got 2 boards. This board is the one that has the 4 buttons on it. So we'll just look at each board, each side, one at a time. So this has the 4 buttons for the 2 volume, the mute, and the power button. And you can see that the mute button has a couple LEDs. So that button illuminates whenever that button is pressed, so you can visually see that the device is muted. This button here is the power button, and you can see that it has a very tiny little sensor right there, and that's a light sensor that allows the Echo Dot to detect the amount of light in the room. And based on the light in the room, it adjusts the brightness of the LEDs that are on the other side that illuminate a ring around the dot. So that's pretty much all there is on this side of the board, just the 4 dome tactile switches, 2 LEDs, and a light sensor. Now on the other side, we have, we have the microphones, so it's directional microphones. There's 7 microphones on here. So you have 1, 2, 3, 4, 5, 6, and then 1 right in the center. Then also along the outside you have the LEDs, RGB LEDs, red, green, and blue, so they can illuminate different colors. So each microphone has 2 LEDs, 1 on each side of it. So you can see those located here. Use a pen. So those are the LEDs, and then that's the microphone. Then on the the core is you have, these are the analog to digital converters. So they take the analog signal coming from the microphones, and then they convert it to a digital signal that can be processed. These are from Texas Instruments. They're a TLV 320 ADC. So there's 4 of them. Each one of these is a 2-channel analog to digital converter. So we have 7 microphones, so we need 7 channels. So they used 4 of these, each with 2, so there's actually 8 channels available, only 7 are used. So one of these has an empty channel that's not being used. Then finally we have this chip here, which is a bit unknown, the exact what component that is. A lot of chips, they don't put the full part number on them. They'll just put a die designator that only the manufacturer understands. That's done in some cases for limited space, but also they want to make it difficult for people in competition to reverse engineer their product. So some things I've read is claiming this is a microcontroller. I tend to think it's more of an LED driver, because it's got to be what drives the LEDs and the brightness of those. There may be, it could be an LED driver that's got some simple functionality that also can detect the buttons, because something is going to need to monitor the status of the buttons, and typically that's kind of a function that's best left for a microcontroller. So this is a little bit of a mystery what this one is, but we're going to say it's a microcontroller / LED driver of some sort. So that's most of it. Then you have some really tiny little devices here that look like chips, but you can tell their die designator is a Q. So Q1, maybe Q2 and Q3. So those are transistors. Those are just discrete transistors is usually the Q. Then you have a really tiny little chip here. It's just labeled U101. I'm not quite sure what that is. It looks like maybe something in like an SC70 package. So based on it's not any type of power regulator because there's no capacitors really associated with it. So I'm not sure what that is. It could be a level shifter or something simple to that nature. And then we have the ribbon cable that connects this board to the motherboard. So these 4 chips here will output a digital signal which is fed through this ribbon cable, and then that is what goes to the motherboard. So that is, let me see if there's anything I think I missed on this board. Obviously you have all the small support capacitors and resistors. That's pretty much what the rest of this is. I don't think there's anything else. Let me see. No, that looks like about it. So yeah, the 4 analog to digital converters, the microphones, the LEDs, and the microcontroller / LED driver, and then a ribbon cable, and then some various transistors and some small unknown microchip. Okay, now we're going to be looking at the main board. This side, you can see there's a shield, which will pop off in a second, and then the other side. So let's maybe start with this other side. So here in the center, you have a digital to analog converter. So on the other board, we had the analog to digital converter. So those took the analog signal from the microphone, converted it to digital format for processing by the CPU. Then to output and play audio, it's the opposite process. So you go from the digital to analog. So this takes the digital output coming from the microprocessor and then converts that to an analog, which is then will be fed into an amplifier and then drives the speaker. So that's what this chip is here. That's the main component, the critical component that's on this side of the board. Obviously you have the ribbon cable connector that connects with the microphone board. You have the USB connector, and then you have the audio connector. And then obviously there's a whole other, quite a few other support components, mostly small capacitors and resistors. But there's also, well, these 2 here look like chips, but those are really capacitors. But there are a couple really tiny chips. There's one, here's one coming off the USB. These, you can't really find out what part number or pull up a data sheet on these. This tiny chip here that's coming off the USB, I'd be willing to bet that's just their protection diodes. So if there's like an ESD event on one of the external USB pins, you don't want that tying directly into a processor and frying a pin. So usually you'll put protection diodes. And then, like I said, there's a few other chips that you can't really identify. That's pretty much that side of the board. And then you get to this side, and this is where all the brains of the product are. I won't say the good stuff because it's all good, but okay. So let's take a look at this. We have 4 primary chips on this side of the board. You have this chip here, which is a MediaTek. That's a Taiwanese company. They're a semiconductor manufacturer, fabless. So means they design the products, but they don't actually have they don't fabricate them themselves. They use a third party. So this is a MediaTek MT6323. And what this is it's a power management IC. So it's got 3 buck regulators on it. So a buck regulator is a switching type of regulator that can take a higher voltage, step that down to a lower voltage. And it does that very efficiently without wasting power. But it also tends to be more complicated than a linear regulator. and you can actually see that these here are inductors. So a switching regulator will require external inductors. So there's two of them there. So this chip can do output three buck regulators, and then it has an astonishing 23 linear regulators, or specifically LDO, which is just low dropout regulator, but they're linear regulators, so they're more simple. Then it's got some other secondary functions like a watchdog timer and various other functions, but the primary function is it's a power management IC, so it provides all the various voltages required for all the components on both of these boards. And then, like I said, all of this is the support circuitry that goes along with it. And you can see that's placed right next to these other chips. It's a switching regulator, so it's switching at high frequency. So anytime you have switching circuits, you always have to be careful that those don't affect other parts of the circuit. Fortunately, the rest of the critical stuff is inside of this shield. So this chip here, this is the processor. So this is it's a MediaTek again. It's a MediaTek MT8163. And what this is this has a quad Cortex A53 processors running at 1.3 gigahertz. It also includes, a graphics processing unit, and then it includes the transceivers for, it has Bluetooth, Wi-Fi, GPS, and an FM transceiver all built into it. So that's this chip here. This chip here is an external memory chip. So this provides 4 gigabytes of flash memory and 512 kilobytes of high-speed SD or DDR3 SD RAM. So this is just a memory chip. So it's got the flash memory for more permanent storage, and then it just has the 512 kilobytes of RAM for temporary storage. And then finally over here we have another chip, and this is a front-end wireless chip. So I've seen other teardowns of the Echo, and they've just referred to this as the wireless module that provides Wi-Fi. There's 4 wireless technologies that the DOT uses, and that's Wi-Fi, Bluetooth, it has a GPS receiver, and then it has an FM receiver. And this is actually not the transceivers for those 4 wireless functions. Those are built into the processor. What this is it's the front end, it's the analog front end for those 4 wireless functions. And a front end just means the circuitry that's sort of on the very front. So this is the main signal coming from the antennas will hook into here. So, and then this provides and I'll look at that. Yeah, I was actually able to find the data sheet for this, so we can pull up the functional block diagram and you can see exactly what this chip does. But it's basically got some amplifiers and RF switches, and then it connects to the antennas, and then the output of this front end chip then goes into the transceivers. The transceiver being Wi-Fi and the Bluetooth, because a transceiver is two-way communication. So Wi-Fi and Bluetooth you can send or receive. GPS and the FM radio are receivers. They're not transceivers. They can't transmit. They can only receive. So that's the purpose of this chip. And you can see they're all underneath sort of the same shield, but these two are isolated, which is exactly what you want. This is going to be running at 1.3 gigahertz. So you don't want that to interfere with any of the RF signals that are connecting up to this chip. This runs at 1.3 gigahertz. The Wi-Fi will run at 2.4 or 5 gigahertz. The Bluetooth runs at 2.4 gigahertz, and the GPS runs at 1.6 gigahertz. Okay, we're going to do a quick recap on all the components. So you have the bottom piece of the enclosure. Then we have, this is we'll just call this a metal weight, which basically just gives the product some weight to make it feel of a higher quality and prevent audio vibrations. Then we have the non-slip silicone rubber pad that is attached through it looks like a double-sided adhesive tape. Then we have just a thin plastic protector that goes under the anti-slip pad. Then we have the USB charger with the USB cord that goes to a micro USB connector. That is for powering the product. Obviously, a lot of you are used to seeing USB chargers are used for recharging a battery. The Echo does not have a battery. It's powered, it requires that it be plugged in all the time, but you can still, whether or not you're charging a battery or powering your product, a USB charger is a great solution for providing a 5-volt DC voltage. Then we have the 4 screws. This is the top plate with the 4 buttons, which is made up of several different pieces of plastic. It has these kind of odd-looking shaped plastic piece here that connects all the buttons and gives them a little bit of spring and holds them in place. Then we have the speaker, which is probably not like any speaker you're used to seeing. It's a small speaker, but it's enclosed in this custom plastic enclosure for amplifying the sound. Then we have a spacer ring, which is just plastic and it goes sort of in between the 2 boards. Then you have a silicone rubber spacer that goes up against this plastic one, and the purpose of this, I suspect, is to prevent vibrations from audio. Then we have the box itself that it came with, which is made out of paperboard. I don't have it here with me, but the insert, the cardboard insert or the paperboard insert that held the pieces in their own little compartment, it's also there. And then finally, you have the 2 boards. You have the microphone LED board with the analog to digital converters. Then you have the 4 buttons that connects through a ribbon cable to the main board, which includes the microprocessor, the Wi-Fi, Bluetooth, GPS, and FM receiver. Then you have a power management IC. And you have on the back, this is the digital to analog converter that takes the digital from the microprocessor, converts it to audio, gains it up, and sends it to the speaker. And then obviously all the small support components, resistors and capacitors mostly. The USB connector, the audio connector, the ribbon cable connector, and then right here are 2 little spring-loaded contacts that make contact with the battery here. And then you have also the shield with the top to it that I had removed. And that just is to prevent, the shield serves 2 purposes. It prevents something from radiating out electromagnetic interference, like say from the processor, but at the same time, it can also shield, like this front end wireless chip here, shields it not only from the noise from the microprocessor, but also the switching regulator, but it also shields it from outside EMF noise. So that's about it. As you can see, it's a very efficiently designed product. Obviously, this is the 2nd generation. The 1st generation was considerably different. I don't want to go into detail on that generation, but as you noticed, the main board here used a lot of MediaTek components versus the 1st generation tended to use, like for instance, instead of this MediaTek microprocessor, it used a TI digital media processor, which was a processor specifically for processing digital media, whether that be sound or video. But that is, so each time, even a company like Amazon, they strived it, they probably went with some more standard solutions for the first version. And then, as time goes on, the product obviously became quite popular, and then they probably went to either optimize it to improve performance or possibly do some cost reductions. There's now a third generation Echo Dot that just came out like a day or two ago. So I'll maybe do a teardown on that in the future. But this is a really good product to look at as a case study. It's not overly complicated, but it's still a fairly complicated design. And it's got a microprocessor instead of a microcontroller, although it probably has a small microcontroller for dealing with the LEDs and the power buttons. But overall, it's going to be a high-speed microprocessor. So it's a fairly complicated design. You can see there's quite a few plastic pieces. So you have, this is the sort of the main enclosure piece. So that's a custom piece of plastic. The top piece, you've got this ring here, that's one piece of plastic. Then you've got this transparent ring, that's another piece of plastic. So that's, what, 3 pieces, 4 for the button, 5 for the springs. Then you've got this piece here, which is, so that's 6 pieces of custom plastic. This is likely 2 pieces of custom plastic, so that's up to 8 pieces now. This is obviously a custom shaped piece of silicone, which is not going to be as complicated or as expensive as a custom, like a hard plastic. And then you've got just this silicone ring that you could just buy that off the shelf. That wouldn't be customized. So overall, you've got, not counting this piece of silicone here, it looks roughly about 8 pieces of custom plastic. Then there's obviously one piece of custom metal, so that would require a separate mold. They're different for plastic. You call them high pressure injection molds. For doing something metal like this, they're called die cast molds. But it's basically the similar process.